Modern AI gets a lot of attention for reading, writing, and understanding text. But long before large language models existed, an invisible algorithm was shaping what we consume, learning your taste without reading a single word. Right here in the NLP and recommendation block sits Algorithm 43, Collaborative Filtering. This is the mathematical engine behind the product recommendations you see every day. It doesn't look at the metadata of a movie or the text of a book. Instead, it relies entirely on past human behavior. It treats content as a complete black box. The goal is mathematically mapping the crowd to predict what an individual person desires next. The need for this math started back in 1994. The early internet was expanding rapidly, and Usenet forums were suddenly drowning users in a chaotic flood of daily articles. There was simply no way to sort good posts from noise. Picture university students sitting at thick CRT monitors, scrolling endlessly through feeds just to find something worth reading. Staring at screens like this, a team of researchers at the University of Minnesota's Group Lens project realized they needed a filter. They settled on a surprisingly simple premise. If two people agreed on which articles were good in the past, they are highly likely to agree again in the future. To test this, they built reading servers called Better Bit Bureaus. These servers collected 1 to 5-star scores from readers, matching users who historically voted the same way. By pooling those opinions, the Group Lens pioneers proved that human preference, as subjective and messy as it feels, could be distilled into a reliable, quantifiable signal. To predict taste, you have to translate that messy human behavior into a geometry that a machine can actually calculate. We start with a network diagram like this one, showing a tangled web of distinct users giving thumbs up and thumbs down ratings to random items. The first step is to organize that web into a grid. This graphic shows a user item matrix. The rows represent people, the columns represent items, and the cells hold numerical ratings from 1 to 5. Next, the algorithm calculates the Pearson correlation to measure the mathematical distance between you and everyone else. Looking at the co-rated items, it identifies your statistical near twins, like Anne at positive 0.99, and your exact opposites, like Bob at negative 0.99. Finally, it calculates a similarity-weighted average of your neighbor's ratings. Because Anne is nearly identical to you and gave Toy Story a 5, the algorithm predicts you will give it a 5, completely ignoring Bob's low score. This is pure content-agnostic mathematics. It correctly predicts an individual's taste simply by crowdsourcing the preferences of their statistical neighbors. But there is a computational ceiling to this method. If a web-scale company tries to calculate the distance between millions of users in real time, the processing cost becomes crushing. This forces a split in recommender system strategies, bringing us to neighborhood-based approaches. The solution, as this slide illustrates, is to flip the matrix by 90 degrees. Instead of searching for similar users, you pre-compute the similarity of the items themselves. This relies on the co-occurrence intuition. If a razor and shaving cream are bought together repeatedly by the same people, the algorithm mathematically links them. It has no idea what shaving is. It just knows those data points travel together. Flipping the axis from users to items allowed platforms like Amazon to scale recommendations across massive global catalogs. Human moods change by the minute, but item relationships stay remarkably stable. In practice, these systems face harsh mathematical realities. In massive catalogs, most users only rate a tiny fraction of items, leaving the matrix mostly blank. This chart lists major limitations, highlighting the sparsity curse and scalability issues of building giant similarity matrices from mostly empty cells. It also notes the cold start vulnerability. When a new user or product is added, the algorithm is completely blind without behavioral history. Despite these flaws, this architecture was robust enough to serve as the baseline for the famous $1 million Netflix prize, challenging engineers worldwide to beat its predictive accuracy. Collaborative filtering laid the groundwork for everything that followed. Its vulnerabilities and sparse data directly drove the invention of the hybrid models and matrix factorization systems that rule our feeds today. We took the messy, subjective problem of human taste and solved it with a rigid matrix of behavior and weighted votes. Next, we will put this into code. We won't look at the script just yet, but implementing this takes only a few lines of pandas. The theoretical math becomes a functional reality the moment we load a dataset of real movie ratings and let correlation do the filtering.
Building a collaborative filtering recommender system, we start with our raw input data. This is typically a narrow list of server locks where each row represents a single interaction, a user ID, a movie ID, and a numerical rating. Since ID numbers are difficult to interpret, we merge this review data with a secondary dataset containing the actual movie titles, using the movie ID as the join key. Here is our first structural requirement. We cannot calculate mathematical similarities on a flat vertical list. We need to reshape this data into a two-dimensional grid to compare every user against every movie. The pivot table command reorients the data, assigning user IDs to rows and movie titles to columns. Look at the empty cells. Since no user watches every movie, the vast majority of these intersections are missing data. This grid represents the core data structure of collaborative filtering. Extracting meaningful patterns from these sparse data points is where the majority of recommendation logic is spent. To generate recommendations for a specific film, like Avatar, we isolate its column in the matrix and search for similarities across the rest of the titles. The core with command calculates the Pearson correlation by comparing our target movie's column against every other column, only for users who rated both. Without access to genres or actors, it relies entirely on behavioral co-ratings to generate similarity scores. Consider why a terrible, obscure movie might accidentally yield a perfect 1.0 correlation with a massive blockbuster. Mathematically, if only 2 users watched an obscure film and happened to rate it identically to the blockbuster, the algorithm calculates a perfect match. That statistical fluke creates a false recommendation. To solve this, we use .join to add a rating count column, then filter out any titles with fewer than 100 total ratings. This removes the anomalies, leaving robust matches like Thor. While correlation math identifies potential candidates, this popularity threshold establishes statistical trust. It shows that raw algorithms require these real-world constraints to be effective. These 10 lines of pandas code handle the entire transformation from raw user logs to behavioral similarity. While this logic works on a local dataset, it reaches its limit at web scale. A matrix that is 99% empty or a brand new user with zero history creates a cold start problem, which requires moving from these simple calculations toward matrix factorization. In mathematics, a correlation matrix is a clever way to find relationships between variables. Back in 2003, Amazon faced a serious computational wall. They needed to predict what their customers might buy next, but their product catalog and user base were expanding too fast for their servers to compare every single shopper against each other. In this animated grid, you can see the solution engineered by Greg Linden, Brent Smith, and Jeremy York. Instead of mapping one user to another user, they mapped the items directly. If someone buys a Harry Potter book, the algorithm simply draws a line straight to a Harry Potter bookmark. By focusing entirely on item-to-item correlation, by October 2006, the financial value of these algorithms was so obvious that Netflix publicly offered $1 million to anyone who could beat their in-house Cinematch system by exactly 10%. To fuel the challenge, they released an enormous trove of data. As these classic red DVD mailers remind us, this was the mid-2000s, yet the dataset contained over 100 million individual movie ratings. The competition ran for years, culminating on June 26, 2009, when a team named Belcore's Pragmatic Chaos finally broke the 10% barrier and claimed the $1 million check. That mathematical arms race permanently cemented the role of collaborative filtering in entertainment. Today, correlation algorithms dictate roughly 75% of everything watched on Netflix globally. However, pure behavior has limits. The red box highlights the cold start problem, and as this feedback loop illustrates, relying solely on historical behavior traps users in echo chambers.
A heavily linked cluster of popular items will continuously cannibalize smaller nodes, shrinking diversity and creating an inescapable popularity bias. Then there is the gray sheep anomaly. If a user has highly eclectic tastes that don't neatly overlap with any specific group, the math fails to find neighbors and leaves them stranded. The system also suffers from context blindness. If you buy an advanced chemistry textbook for a required college class, the algorithm assumes you read industrial science for fun, poisoning your profile. Pure behavioral math breaks down the exact moment human action separates from genuine personal preference. Because of these blind spots, modern engineering requires a multi-layered approach. This flowchart places collaborative filtering centrally. Looking at the neighboring branches, we see failsafes. Engineers switch to hybrid or content-based approaches to handle sparse data. This architectural breakdown comes from 50 Algorithms Every Programmer Should Know by Imran Ahmed, a great resource for seeing how these systems fit together. Curious, leaning in, but an enormous engineering question remains. When you have a grid like this one, representing millions of users and products, yet 99% empty, how do you compress those sparse behaviors down into dense, usable mathematics? The answer lies in the next evolution of recommendation systems, matrix factorization, and that algorithm is exactly what we will unpack next time.